start moving these particles at relativistic speeds, so that v is of order c, then the energies that you're considering are of order mc squared. And at these energies, it is kinematically possible. That is to say, it is consistent with conservation of energy to create a new particle. So if you have a particle moving at relativistic speeds that is undergoing some interactions with something else, say, then the typical energy is of order mc squared. And once energies are of order mc squared, it's possible energetically to create some new particle, to imagine some new particle popping out of nothing being created in this process. Okay. And so what that means is that we really need to be considering, when we talk about relativistic quantum mechanics, theories where you have not just one particle, but where you have the possibility of creating or destroying particles. So in relativistic quantum mechanics, we are first to consider processes where particles can be created or destroyed. If you think about our, for example, description of an electron moving in the hydrogen atom, then we solve that Schrödinger equation in 3 dimensions. We use spherical symmetry to reduce it to a 1-dimensional problem, but we're always solving the problem where you have exactly 1 electron. Now, in a real hydrogen atom, you would have many electrons, and so you would fill up the energy levels using the Pauli exclusion principle. But at the end of the day, we're only ever studying a theory, we're only ever studying a system where you have a fixed number of electrons. You're not considering in that system the possibility that electrons could be created or destroyed. In particular, when we describe the Hilbert space, say, of n electrons in the hydrogen atom, n is a fixed number that describes our Hilbert space. When we start talking about relativistic quantum mechanics, we're going to have to construct a much larger Hilbert space. A Hilbert space that describes the possible states of the system with 1 particle, 2 particles, 3 particles, and so forth. And that's completely necessary just because you can see that relativistic corrections are important if and only if the possibility of creating a new particle is important. Just to say this a little more precisely, one can imagine, for example, particles that are moving very slow compared to the speed of light, and then you can imagine trying to calculate the size of relativistic corrections to, for example, the energy levels of the system. So one way you could try and get around this argument is you could argue, you could try and ask whether relativistic corrections to, for example, energy levels are comparable to those due to multiparticle states. So, for example, you can imagine some process where you have an electron moving at 1/10 the speed of light, okay, so that mv squared, the energy would not be mc squared, but would be 1% of mc squared. And when you could say, well, that's less than mc squared, so you would think that it would be impossible to create a new electron. So you might think that if you're studying an electron moving at 1/10 the speed of light, you could completely ignore the possibility that a new electron could be created. Okay. But in fact, that still isn't going to be good enough. Because you can see, for example, that the relativistic kinematics, by which I mean the equation for energy in special relativity. So, just to remind you, if you have a particle moving with some momentum p and with a rest mass m, then the energy of that object in special relativity is given by the square root of m squared c to the 4th plus p squared c squared. So you can see that this reduces down to, when p is equal to 0, m squared, mc squared. And then you can Taylor expand for small values of p, and the first term in that expansion is the usual kinetic term 1/2 mp squared, or 1/2 mp squared, plus various relativistic corrections. And then you could ask, what would be the typical size of the correction due to this formula to, for example, the energy levels of some system? And the correction will be of order d squared over c squared. That's just because that's the usual relativistic gamma factor. That's the usual factor that controls the size of subsequent terms in this subleading expansion. So these dot 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 terms are suppressed by powers of e squared over c squared. Hopefully you'll remember that. That's the standard thing that always happens in special relativity. Whereas the corrections due to multiparticle states can be estimated simply by noting that if you have some multiparticle state, then, for example, the change in some energy level due to the presence of some multiparticle state. So let's say that, so just to be a little more explicit, let's say that you're adding some correction term to your Hamiltonian, then the usual formula in time-independent perturbation theory says that the correction to ground state energy due to this perturbation has one term, which is just the correction to the Hamiltonian. That's this correction of order d squared over c squared that we wrote down up here. But it also has other terms coming from the other states in the system. And what does this mean? This means that if you have multiparticle states in the system, they'll contribute to the corrections to this energy to the ground state energy, even if you do not never considering a process where you have enough energy to actually create a new particle. So the presence of multiparticle states in the Hilbert space will lead to corrections. And the typical size of these corrections will be of order the typical energy of the process that you're considering divided by the energy of a multiparticle state. which will be of order mv squared over mc squared. So that's also of order v squared over c squared. So what this argument is telling us is that we should suspect, based on this, that a single particle theory of relativistic quantum mechanics shouldn't make sense on its own. In particular, if you just try and describe the Hilbert space of a single particle, using the formula, for example, using some relativistic formula for the energy instead of a non-relativistic formula for the energy, then you would expect that Hilbert space, that the predictions of that single particle relativistic quantum mechanics will not be a good match to reality, because the corrections due to multiparticle states would be of the same order as the relativistic corrections due to that single particle relativistic quantum system. In fact, I would like to argue, so I would like to make this a little bit more specific, and I'll show you that, in fact, a single particle relativistic theory of quantum mechanics is impossible. And in particular, what I'll argue to you is that if you try and construct a single particle theory of quantum mechanics, at least just following your nose and using the standard rules of relativistic quantum mechanics, you'll quickly run into a contradiction. You'll find that it's possible to go back in time and kill your grandmother. And that is going to force us, in trying to develop a theory of relativistic quantum mechanics that is consistent with causality, to consider a multiparticle theory. And then there are a variety of ways that one can go about and construct such a multiparticle theory. And over the next two lectures, after this one, I'll briefly sketch two of them. One leads to what is known as scalar field theory. The other leads to the relativistic field theory, the relativistic theory of quantum mechanics that describes electrons. So that's given by Dirac's equation. And so we'll go through and develop the theory of Dirac's equation and use it to make some remarkable predictions. So, for example, we'll be able to predict the anomalous magnetic moment of the electron, and simply based on some straightforward applications of relativity to quantum mechanics. So today, however, what I want to do is I want to convince you that single particle relativistic quantum mechanics makes no sense. And so that is what we're going to try and do first. Before I do so, let me pause and see if there are any questions. Okay, that is what we're going to describe. Okay. So let's consider a single particle Hilbert space. So in non-relativistic quantum mechanics, how would we describe that? Well, you would have a Hamiltonian, which is 1 over 2m times p squared, and you would describe the Hilbert space, that is to say the basis of states, and momentum space. You would, by constructing some set of states that are eigenstates of the momentum operator, labeled by a momentum k, and then the energy of one of these states, of course, so these states are energy eigenstates, and the energy of one of these states would be 1 over 2m times k squared. So this is the entire theory of a free particle in non-relativistic quantum mechanics. So what happens then if we take the same Hilbert space, namely the same Hilbert space which has at its basis the momentum eigenstates, each labeled by a momentum vector k, but with the relativistic Hamiltonian, where the energy of the state is determined not by the non-relativistic formula 1 over 2 mp squared, but by the relativistic formula n the squared of n squared c to the fourth plus p squared c squared. So far in your lives as quantum mechanics, you have not considered Hamiltonians, where you have some sort of complicated square root that appears in the expression for the Hamiltonian as a function of momentum. That is to say, you've considered dispersion relations, so relations between energy and momentum that involve simple integer powers of the momentum, for example. And our goal then is to ask, what happens if we try and generalize our theory of quantum mechanics to include such a Hamiltonian, which would be indeed what I mean when I say the relativistic single particle quantum system. So to clear what I mean by this, so for example, our basis of states, again, is given by these momentum eigenstates, and these states will be eigenstates of the Hamiltonian with eigenvalues that I'll just call omega. So that's the square root of m squared c to the fourth plus k squared c squared. So let's now explore this theory and see if it really makes sense. So in particular, what I'm going to do for the rest of this lecture, just to make our lives easier, I'm going to use units where c is equal to 1, just meaning that, for example, I measure distances in light seconds and time in seconds, for example. And also, just to keep our lives easier, I'll set h bar equals to 1 either. Again, that just means that we're using units where, for example, energy is measured in units of 1 over time, or momentum is measured in units of 1 over space. So, for example, time could be measured in seconds, distances in light seconds, and momentum in h bar divided by light seconds, if you want to say it that way. says that these momentum eigenstates have energies which are given by the square root of m squared plus k squared. Okay. So far I've been looking at this theory in position space. What happens if we look at it? So far I've been looking at it in momentum space. What happens if I look at it in position space? So in particular, the quantity that I'm interested in trying to compute is the amplitude for a particle sitting at the origin at time t equals 0 to propagate to some other point that I've called x here after some time t. So this is what we know as a propagator. Of course, I could try and compute it using a path integral if I like. This is a quadratic theory, so I could do that if I wanted to. But, of course, I can also do it much more simply just by computing it directly using our form of the Hamiltonian. So here I'm using 0 vector just to denote, maybe I should, that's not a very good notation. Let me just say the point where x is equal to 0. So this is the probability, or the amplitude for a particle to move a distance x in some time t. So the way that I'm going to do this is I'm going to insert a complete basis of states. And I'm going to use the fact that our Hamiltonian is diagonal in this momentum space basis. So what is that? That's the integral d3k times the wave. So this guy here is the wave function e to the I k dot x. And then here I can use the fact that this bra vector, this bra k, is an eigenstate of the Hamiltonian. And so I get minus I times omega sub k t times the wave function of, again, the wave functions in momentum space, e to the ikx, evaluated at x equals 0, which is just 1. So this is the integral that I need to compute. And the first thing that I'm going to do in computing this integral is I'm going to choose, so I need to perform this integral over the 3k coordinates. And I'll just choose a basis where the vector x points in the z hat direction. So of course you know by rotational invariance, I'm always free to choose my coordinate axes however I like. At the end of the day, the answer that I get should depend only on the distance between the origin and the point x and not on anything else. So I'm free to make that choice. Then I can write this out in spherical coordinates. So I'll denote by k without a vector symbol the length of the vector k. And then I have the theta and phi coordinates in momentum space or in k space. So the theta coordinate is the angle off of the z-axis. And we have our usual Jacobian integration measure factor that arises when you work in spherical coordinates. And then you have the azimuthal angle, maybe it's, well, I forget actually what it's called. You have the other angle phi, the one that tells you the angle in the xy plane. And then you have this exponential factor. So you have the e to the minus I omega sub k t plus I times k dot x, which is just the length of the vector k times r times cosine theta. So in your mind, you should think of the vector x as pointing in the z-hat direction. So here's the x-hat direction. I'm using x in two different ways here, but hopefully you understand what I mean. Here's your vector k. There's the angle theta. And then you have this angle. Sorry, that's not a very good picture, but you know what spherical coordinates look like. I don't need to tell you much more about that. What's that? They don't work. Did I label them the wrong way? Yeah, I can never tell left from right. I'm mildly dyslexic in that. Okay, point of view. Okay, so here's phi. Something like that. Okay. I can also never remember if phi is the angle off the x-axis or the y-axis or whatever, but you're smart. You guys can figure that out. Okay. Is that, okay, I feel like that diagram's so messy, it just makes things worse. But you understand what I mean here? Just going to spherical coordinates? Okay, good. Okay. So the nice thing to notice is that omega k is the square root of k squared plus m squared is independent of theta and phi. So I can just pull it through, so I get an integral from 0 to infinity, k squared dk, e to the minus I, omega kt. I can do the phi integral, so again I get some factor of 2 pi. And then I have the theta integral. So what is that theta integral? That's the integral from 0 to pi of d theta sine theta, or just the integral, if I want to write it this way, from minus 1 to 1 times d of cosine theta times e to the I kr cosine theta. So I can then just do that integral. It gives me a factor of 1 over I kr, so which kills one of the factors of k. And I have the result of that integral, so e to the I kr, from the one end of the range of integration and e to the minus I kr from the other end of the integration. So this is the amplitude to propagate a distance r in a time t. And what we would like to ask is what happens when r is bigger than t, i.e. when the point x just as a reminder, if you don't remember the terminology from special relativity, we say that points are space-like separated when you can't get from one to the other without traveling faster than the speed of light. Okay. I.e., one would have to travel at velocities greater than c to get from the origin to the point, a distance r from the origin. Okay, so let's then stare at this integrand and think about what it looks like when we have r bigger than t. Okay. So this transition probability, this propagator, I'll just rewrite that for you. What was that? 2 pi over IR, integral k dk, e to the minus I times omega k, which is the square root of m squared plus k squared times t times e to the ikr minus e to the minus ikr. Okay. So the way that I would like to think about this integral, I'm not even going to bother to compute it for you explicitly, but what I will show you is that this integral is non-zero, which is enough to conclude that our theory is actually quite sick. And the easiest way to see that this integral is non-zero is actually to think about this integral in the complex R plane. So in particular, we would like to deform the contour of integration. So what does the integrand look like in the complex R plane? So we're integrating along the real R axis from 0 to infinity. Oh, yeah, I actually skipped one step. So the integral up here is the integral as k goes from 0 to infinity, but I can write that just by noting that this term is related to that term by taking r to minus r. I can write this just as the integral of e to the ikr, where k is integrated from minus infinity to infinity. And so then, sorry, said something incorrect earlier. We want to imagine doing this integral by deforming the contour of integration in the complex k plane. Sorry, I don't know why I said complex R plane. I haven't enough coffee yet this morning. Okay, is everything clear so far? So we're calculating the amplitude to go distance r in a time t. We've reduced it to a one-dimensional integral of this quantity dk, and that integral is along the real axis in the complex k plane. And let's stare at the integrand and think about what it looks like in the complex k plane. So the first thing to notice, so we start by doing the integral here along the real k axis. And the first thing to notice is that since r is bigger than t, the integrand vanishes when the magnitude of k, when the absolute value of the complex number k goes to infinity, if it has imaginary part which is larger than 0. So in particular, you could imagine deforming this contour of integration that I have written here. And what we see is that if you deform it into the upper half of the complex k plane, then out at infinity, that contour will vanish, or that integrand will vanish, just because r is bigger than t. So in particular, you can imagine trying to push the contour all the way up here, up at infinite values of the absolute value of k, and because we pushed it into the upper half of the complex k plane, the integrand will vanish exactly. So you might therefore think that the integrand is exactly 0. Okay. And that would be great, because that would mean that our particles can't travel faster than the speed of light. But there's a little bit of a subtlety here, which is that the function that you're looking at here has a branch cut, because it has a square root. And there will be two branch points at k is equal to im and minus im. And there will be branch cuts going off to infinity from there. So that when you do this contour integral, when you deform the contour, you need to take into account the fact that your function is crossing this branch cut at large imaginary values of k. And so the easiest way to take that into account is to deform your contour integration so that it goes around the branch cut like that. And then the contribution that you get to the integral will just come from the integration along the branch cut. So in order to perform the integral along the branch cut, let's just let k be equal to iz, and then we want to perform the integral where z runs from m to infinity. So this is 2 pi over ir, so there'll be two factors of I coming from this factor of I that occurs when you change variables. So z dz, and then we just need to write down the integrand when with z replaced by k, with k replaced by z, and so you have e to the zm, sorry, zr, coming from this term here. Actually, we need to be, e to the zr. And then we need to integrate the difference between the two, we need to integrate the difference between the function on this side of the branch cut and the function on that side of the branch cut. What is that? That's e to the square root of z squared minus n squared t. That's the function on one side of the branch cut, minus the thing that you get on the other side of the branch cut, where the square root has the opposite sign. Or, just to write this out a little bit